So you did it. You've poured hours, maybe even days, into building your AI model. It's finally spitting out predictions. But here's the real question, the one that actually matters. Is it any good? Are those predictions accurate? Are they reliable? Or are you just looking at a bunch of random noise? Today, we're going to put on our detective hats and crack the case on your model's performance. And look, this isn't just about ticking some technical box. This is the difference between a model that can actually solve a problem and one that's, well, basically useless. We need to be able to measure it, to put a number on it, to know for sure. So let's figure out how.
Let's imagine for a second you're trying to predict the length of a flower's petal just by looking at its width. Your AI draws a line, that's its best guess. The absolute heart of our investigation is measuring the gap between that prediction line and where the actual real-world petals are. That gap, that's our first clue. We call it the error.
Right, so this idea of error is at the center of everything. We need to figure out how to measure it, and that brings us to our first big challenge, the prediction problem. Every single metric we're about to look at is really just a different way of looking at this one simple concept, the error. Or if you want to sound like a data pro, the residual. It's just the distance between what your model guessed would happen and what actually happened. This is our primary piece of evidence.
Okay, so now we've got all these errors, a whole crime scene full of them, right? What's the first thing a detective does? They look for a pattern. So let's start with the most obvious approach. Let's just average them all out.
Our first tool in the kit is the mean absolute error, or MAE. Think of it as the honest, no-frills detective. It just takes every single error, ignores whether it was too high or too low, that's the absolute part, and gives you the straight-up average. So if your MAE for predicting house prices is, say, $10,000, it just means that, on average, your predictions are off by 10 grand. Simple, clean, and a really great place to start our investigation.
But what if some mistakes are, well, what if they're way worse than others? What if being off by $100,000 on a house price is an absolute catastrophe? Our next couple of tools take a much, much tougher stance on those big screw-ups.
And this is where things get really interesting. See, while MAE treats a small error and a big error with the same logic, our next metric does something pretty dramatic. It squares the error. A tiny mistake of 2 becomes 4. No big deal. But a huge error of 10? Whoa, that becomes 100. It just blows up the big mistakes, putting them right under a spotlight.
This is the mean squared error, or MSE. I like to think of it as the strict judge, the tough prosecutor of our metrics. It absolutely hates large errors, and it will punish your model severely for making them. And you know what? That's actually super useful when you're training your model, because it forces it to avoid those massive, embarrassing blunders that could totally sink your whole project.
But hang on a second. If we're predicting house prices in dollars, MSE gives us an error in dollars squared? What on earth is a square dollar? You can't go to your boss and say, hey, our model is off by 900 square dollars. It's meaningless, right?
And that's exactly why we have our next tool, the root mean squared error, or RMSE. It's so simple. It's just the square root of the MSE. It does the same job of punishing big errors, but then it translates that final number back into units we can actually understand, like dollars or centimeters. So now we can say our model is off by, say, $300 on average, while still giving more weight to those bigger mistakes. It's really the best of both worlds, a tough judge and a clear communicator.
Okay, so we know our model is off by an average of, let's say, $300. Is that good? Is it terrible? How would we even know? Without some context, that number is just floating in space. We need a reality check. We need a baseline to compare it to.
And for that, we have R-squared. This is our ultimate reality check. It asks a really simple and kind of brutal question. Is your fancy, complicated AI model any better than a model that just guesses the average price for every single house? An R-squared score of 1 means your model is perfect. A score of 0 means, well, it means your model is no better than just guessing the average. It's humbling, for sure, but it's absolutely essential. And just look at this. It's so clear. The baseline model, the one that just guesses the average every time, has an R-squared of 0. But our model, it scores a 0.85. This isn't just a number, it's a story. It's a powerful visual that shows just how much value our model is actually creating. We're not just guessing anymore, we are predicting with way more accuracy.
So what does that 0.85 times really tell us? It means our model can explain 85% of the variation, the ups and downs, in the house prices. It's a measure of how much of the why behind the data our model has actually figured out. It's not just predicting, it's starting to understand.
Okay, we've got our metrics, we have our MAE, our MSE, our R-squared. Everything looks good. Time to pop the champagne, right? Well, not so fast. Because the numbers, as helpful as they are, can be deceiving. There could be a serious flaw hiding in our model that these metrics alone just can't see. A great R-squared score can be like the tip of an iceberg. It looks great on the surface, but it could be hiding some really serious problems underneath. To be a true data detective, we have to go beyond the numbers and look at the evidence with our own 2 eyes. And this is our smoking gun, the residual plot. This is where you literally plot your predictions against your errors. What you want to see, what you pray you see, is a beautiful, random, totally boring scatter of dots. That means your errors are unpredictable, which is perfect. But if you see a pattern, like a menacing funnel shape, a sinister curve, or some crazy outlier way off on its own, that is a huge red flag. It means your model has a hidden bias, a systematic problem that could be leading you to some really bad conclusions.
Seriously, if you remember one single thing from our entire investigation today, let it be this. Always, always plot your residuals. It is the golden rule. It is the single most powerful diagnostic tool you have to find out if your model is a genius or, well, a fraud.
All right, we've gathered our numerical clues, we've examined our visual evidence, we've interrogated our model from every possible angle. Now it's time for the final step, deciding which metric we're going to use to tell the story.
So here it is, your detective's cheat sheet. Use my when you need a simple, robust average, and a few big mistakes aren't a total disaster. Use MSE to hammer your model during training, to really force it to avoid those huge errors. Use RMSE when you need to talk about your model's error in a way that everyone can actually understand. And use R² for that quick reality check to see how much better you're doing than just a simple guess. At the end of the day, there is no single best metric. Each one is just a different lens, a different tool to help you see your model's performance. The real skill of a data detective is knowing which lens to look through to find the truth. You've got the toolkit now. The only question left is, which one will you trust to tell the